Oxford, a mathematics building with no name on the front, only a carved stone triangle above the entrance, and Penrose tiles inlaid into the floor of the lobby. Roger Penrose, Emeritus Rouse Ball, Professor of Mathematics at the University of Oxford, and the man whose January 1965 paper on gravitational collapse is still regarded by the Nobel Committee as the most important contribution to general relativity since Einstein, was working on a problem that had nothing to do with his Nobel Prize work. He had been working on it for 20 years. His Nobel Prize work, the singularity theorem that proved black holes are not hypothetical objects, but an inevitable physical consequence of general relativity, had reshaped cosmology. That work was finished. This problem was different, quieter, and in Penrose's view, more fundamental. In 2010, speaking to a reporter after the publication of his book, Cycles of Time, Penrose stated plainly that the Big Bang is the remote future of a previous eon, and that this is real physics, not just hypothetical mathematics. He believed our universe was not the first. The standard model of cosmology treats the Big Bang as a beginning, the singular moment from which space, time, matter, and energy emerged. Penrose had spent 2 decades building a mathematical case for why that cannot be the whole story. The problem is entropy. The Big Bang did not start in disorder. Physicists have known this for decades, and almost none of them like to discuss what it implies. The universe that emerged 13.8 billion years ago from a single infinitely compressed point was not random. It was extraordinarily, improbably ordered, a configuration of matter and energy so specifically arranged that its existence by random chance approaches mathematical impossibility. In his 2004 book, The Road to Reality, Penrose calculated the probability of that initial state arising by chance. He used the Bekenstein-Hawking formula for black hole entropy to determine the maximum possible entropy of a universe the size of ours, then compared it to the entropy at the Big Bang. The answer is 1 in 10 to the power of 10 to the power of 123. That number cannot be written down. The observable universe contains approximately 10 to the power of 80 atoms, and the physical space those atoms occupy is not large enough to hold every digit of Penrose's denominator written in sequence. A googolplex, 10 to the power of 10 to the power of 100, already a number with no physical representation, is smaller. Physics has a working answer for the initial conditions problem, cosmic inflation. Inflation was first proposed by Alan Guth at the Massachusetts Institute of Technology in 1979, and it is now a cornerstone of the standard lambda CDM model. Inflation posits that a fraction of a second after the Big Bang, an exponential expansion of space smoothed out any initial disorder, stretching whatever conditions existed before into the flat, uniform universe we observe today. The mathematics work. Inflation explains why regions of the sky that should never have been in causal contact look identical. It accounts for the large-scale structure of galaxies and the observed flatness of space-time. On those counts, its predictions have been well confirmed. What inflation does not account for is the inflaton field itself, the specific scalar field with specific properties that drove the expansion, whose own initial conditions remain unexplained. Inflation pushed the question backward. It did not close it. Penrose had been making this argument since the 1980s, and most of his colleagues acknowledged it and moved on. The problem had no accepted solution. The field had learned to live with it. Penrose had not. The entropy problem sat in the literature, acknowledged in passing, treated as a second-order concern by a field with more tractable questions to pursue. His conclusion, after 2 decades of mathematical work: the extraordinary initial conditions of our universe were not produced by inflation and were not random. They were inherited. When a universe reaches the end of its life, after all matter has decayed, after every supermassive black hole has evaporated through Hawking radiation over timescales on the order of 10 to the power of 100 years, what remains is massless particles and gravitational radiation. A universe that has forgotten how to keep time. Without mass, there is no clock. Without a clock, there is no scale. The infinitely expanded, cold, featureless far future of a dying universe is, in conformal geometry, mathematically identical to the hot, infinitely compressed state of a new Big Bang. They are the same geometric object, separated only by a rescaling that carries no physical information in a universe that can no longer measure itself. The end of one eon does not stop. It becomes the beginning of the next. Penrose presented this theory, Conformal Cyclic Cosmology, CCC, at an academic conference in 2005. He published it in full in his 2010 book. He told physicists the precise observational signature they should look for, the specific measurable traces the universe that preceded ours would have left in the sky. This is what most summaries of CCC left out entirely. Penrose had not merely theorized a previous universe, he had predicted exactly what instruments would detect if it existed. The signal, he said, was in the cosmic microwave background. The cosmic microwave background is the thermal radiation that fills the entire sky. It is the afterglow of the Big Bang, released 400,000 years after that event, when the universe first cooled enough for atoms to form and photons to travel freely. Every cosmologist in the world uses cosmic microwave background data. It is the oldest light in existence, and it carries the imprint of every large-scale structure in the universe's first moments. If a previous universe left any physical trace of itself in our cosmos, Penrose argued, the cosmic microwave background is where it would be embedded. NASA had been mapping it at fine resolution since 2001 with the Wilkinson Microwave Anisotropy Probe. Supermassive black holes in the previous eon, Penrose argued, would have collided with each other in the final epochs of that earlier universe. Those collisions would have radiated gravitational waves outward in spherical shells. Those shells, carried across the conformal boundary between eons into our universe, would arrive embedded in the cosmic microwave background sky as faint concentric rings of anomalously low temperature variance, circles of unusual smoothness fixed at specific points across the sky. In November 2010, Penrose and Vahe Gurzadyan of the Yerevan Physics Institute in Armenia published an analysis of Wilkinson Microwave Anisotropy probe data. They found the rings. Their reported statistical significance was 6 sigma. In experimental physics, 5 sigma is the standard threshold for a formal discovery claim. At 6 sigma, the probability that the result is random noise falls below 1 in a billion. 3 independent teams reviewed the data within weeks. Wehuus and Eriksson at the University of Oslo, Moss, Scott and Zebin at the University of British Columbia, and Gurzadyan in the United States each published independent analyses in late 2010 and early 2011. All 3 reached the same conclusion. The rings were real cosmic microwave background features, but they appeared just as frequently in standard lambda CDM simulations when those simulations were built with the correct power spectrum. The 6 sigma significance had rested on comparison simulations that were too simple. The official scientific record entered the concentric circles as consistent with standard cosmology. Penrose published a new analysis in 2013. He and Gurzadyan identified what they described as concentrated families of concentric rings. Grouped clusters with non-Gaussian temperature distributions appeared, distributions that no purely random cosmic microwave background sky would produce at the observed rate. A separate independent team confirmed in 2015 that the rings were physically real in Planck satellite data. That team also contested their statistical significance. The record stayed open. In August 2018, Penrose published a new paper with entirely different evidence. Working with Daniel An of SUNY Maritime College in New York, Krzysztof Meissner of the Faculty of Physics at the University of Warsaw, and Paweł Narowski of the Center for Theoretical Physics at the Polish Academy of Sciences, Penrose identified a different signature in the Planck satellite data. Not rings of low temperature variance, hot spots. Conformal cyclic cosmology predicted them with precision. It predicted the evaporation of supermassive black holes at the end of the previous aeon. Black holes with masses up to 10 to the power of 14 times the mass of our Sun would have released vast quantities of Hawking radiation. That radiation, vanishingly faint at emission, would have been concentrated by the conformal compression of all subsequent cosmic time into a single ionic crossover point. The result visible in our cosmic microwave background was anomalous circular patches of slightly elevated temperature. Penrose named them Hawking points. They had angular diameters between 3 and 4 degrees, roughly 8 times the apparent diameter of the Moon as seen from Earth. The team found them in Planck 70 GHz satellite data. The confidence level was 99.4%. The same anomalous hotspots were then confirmed at precisely the same sky coordinates in independent WMAP data. Planck and WMAP were built on different instruments with different noise architectures and different calibration systems. The probability of instrument-specific artifacts appearing at identical positions in both datasets is, by the team's analysis, negligibly small. The paper was accepted by the monthly notices of the Royal Astronomical Society in June 2020 and published in July 2020. 3 weeks after publication, the Royal Swedish Academy of Sciences called Oxford. On October 6, 2020, Roger Penrose received the Nobel Prize in Physics. The prize was for the 1965 singularity theorem, not for conformal cyclic cosmology. In an interview with The Telegraph on the day of the announcement, Penrose said that there was something before the Big Bang, and that something is what we will have in our future. He was 89 years old. He had been saying a version of that sentence for 15 years. The mainstream cosmological community's response to the MNRAS Hawking points paper came quickly. An independent analysis found that the Hawking points were consistent with standard inflation once the look elsewhere effect was properly applied, the statistical correction required when a hypothesis is tested across dozens of different parameter configurations simultaneously. The reported 99.4% confidence after that correction narrows to approximately 1 in 50. The European Space Agency and NASA, whose satellites produce the data at the center of the entire dispute, have not issued formal statements on whether the anomalous cosmic microwave background hotspots represent a genuine pre-Big Bang signal. Official communications from both agencies continue to describe the standard model, including inflation, as the accepted cosmological framework. For any discrepancy between that model and the observed data, both agencies have used the same word consistently: tension. That word is not a neutral descriptor. It is the precise institutional language for a finding that has survived multiple rebuttals without being definitively closed, the holding position for a result that cannot be dismissed and has not been accommodated. Penrose found a third line of unexplained evidence in 2017, not in satellite cosmic microwave background data, but in the recorded noise of the LIGO gravitational wave detectors. The two LIGO instruments in Hanford, Washington and Livingston, Louisiana had detected correlated noise patterns appearing in both detectors with the same time delay as actual gravitational wave signals. In a paper published on RxSieve in July 2017, Penrose proposed that this correlated noise was not an instrumental artifact, but a real physical signal. The gravitational wave emissions from the decay of dark matter particles predicted by Conformal Cyclic Cosmology that he named eribons. Each eribon carries a mass of approximately 10 to the minus 5 grams, the Planck mass, approximately the mass of a grain of sand, and approximately 22 orders of magnitude heavier than a proton. By 2020, Penrose had presented 3 separate bodies of observational evidence across 3 distinct instrumental platforms: concentric circles in WMAP data, Hawking points confirmed in both Planck and WMAP simultaneously, and correlated noise patterns in LIGO. Mainstream cosmology produced a rebuttal for each. The case remained open after every one of them. In November 2025, an academic analysis titled "The Physics of Conformal Cyclic Cosmology: Was Roger Penrose Correct?" all along reviewed the full mathematical structure of conformal cyclic cosmology, the conformal matching conditions at aeonic boundaries, the gravitational wave dissipation, the entropy flow between cycles, and the Hawking point signatures in cosmic microwave background data. Its conclusion: the mathematical framework remains scientifically tenable, even where the specific observational detections remain disputed. Mainstream cosmology has never declared conformal cyclic cosmology false. It has declared, consistently, that the evidence is insufficient. Those are not the same verdict. The distinction matters because the problem that drove Penrose to build conformal cyclic cosmology in the first place has not been solved by any competing framework. The initial entropy of the Big Bang, 1 in 10 to the power of 10 to the power of 123, has not been explained by inflation, string theory, or any cosmological model currently accepted by the mainstream. This unexplained number is the core challenge Penrose set out to address. If Penrose is correct, our universe is not a beginning. It is one chapter in a sequence with no first page, preceded by a universe that rose, expanded, and fell over a span of 10 to the power of 100 years, and followed, long after every star in this universe has burned out, by another universe still. Every discovery ever made, every measurement ever recorded, every thought that has ever formed, all of it exists inside one aeon in an infinite succession. Roger Penrose, the man who proved black holes were inevitable at a time when most physicists doubted they existed, still working at Oxford at the age of 93, is insisting that the evidence for this is embedded in the faintest signals our instruments can read. His critics have not proved him wrong. They have argued the signals are not yet strong enough. In science, those are different conclusions. Daniel Ahn, Krzysztof Meissner, and Paweł Norowski confirmed the Hawking points at 99.4% confidence in Planck's satellite data and verified them at the same sky coordinates in WMAP. That data is in the archive. The sky those signals came from is still there, fixed and unchanged, waiting for the next generation of instruments. After 20 years, 3 bodies of evidence, and dozens of published rebuttals, the official record still lists the cosmic microwave background anomalies Penrose identified as unexplained. The European Space Agency confirms that the Planck data containing the Hawking points remains in the scientific record with no definitive closing statement. As gravitational wave detectors increase in sensitivity, and as cosmic microwave background mapping missions improve in resolution, silence from institutions is not reassurance. The question Penrose opened is not historical. It is the question physics will have to answer next. Are we prepared to hear what the next instrument finds?